Okay, so for the last lesson, we've covered these sorts of points now. So we've talked about forces, resultant forces, maybe with one particle, whether that's a horizontal thing or a vertical thing, connected particles. The trick here was looking at the thing as a whole and then sort of picking one part in particular. And if you have lift questions, again, look at the whole thing as a whole. And then when you have these, what does A do to B and B do to the scale pan and all this sort of stuff, start with the top block and work your way down. Okay, we're going to talk now about pulleys then. So what do pulleys do? Well, pulleys use tension. So we're going to see the force of T again. And we've got a situation here. So somebody sort of pulling a box. So tension, um, tension's pulling it up there as the person pulls down. So it's accelerating sort of upwards and through. But we're going to look at a situation where it's just one particle on this side and another particle on the other side. So let's take a look at this question. Sort of another one that you need to learn, another distinct one to learn for this topic. So particles P and Q of masses 2m. Now, that's not a mistake. 2m, the m is unknown. We don't know what that is. And 3m, so 3 times the same mystery number. They're attached to the ends of a light inextensible string. We've talked about this light inextensible string, and we've said that that means acceleration is the same throughout. The string passes over a smooth, smooth, meaning there's no friction, fixed pulley, and the masses hang with the string taut. If it's taut, it means there's no slack, okay? So it's sort of stretched out as far as it goes, I suppose, the string, okay? There's no slack in it. Tension is going to apply. The system is released from rest. We've talked about from rest. You need to be very careful about that word because it may mean later on that u equals 0 in a SUVAT question. So what does it look like? Something like this, okay? You have the pulley, you have block P, which is 2m, and block Q, which is 3m. It says the whole thing starts at rest. And then it says the system is released. So the system is released from rest. I want you to think about very quickly, if you were holding this and then you suddenly let go, what would happen? Well, it would go down to the right-hand side. Assuming that m is a positive, well, it has to be a positive, doesn't it? Because it's mass. It will go down to the right-hand side. So we'll draw all the forces on it, which is something that we do. So 3m is its mass, so 3mg is its weight. 2m is its mass, so 2mg is the weight. There's also tension in the string. The string is sort of holding both of them, stopping them from hitting the ground. So the tension arrows go this way. Later on, we'll talk about the pulley. Don't worry too much about the pulley for now. That's sort of going to come later. So the force diagram would look like this. But we said the heavier one will pull downwards. And we said the heavier one is the right-hand side. So it will start to sort of go like this. So acceleration, it makes sense that acceleration goes down here. In other words, the whole thing sort of accelerates up and down to the right. Okay, so up from the left and down to the right. That's how it should be going. And what that helps you do is that helps you put a direction on all your forces. So accelerates up on the left and around the pulley and then down to the right. And then you normally make two equations. You normally make an equation about P and an equation about Q. So you just look directly at that part and you say what's happening. So what's happening to P? Well, T is the leading force because up on is the direction there. And it's held back by 2mg. So if you use F equals ma, P, this is its resultant force. T is the leading force and 2mg holds it back. And it's equal to m. The m is 2m. So you get that equation there. Do the same for Q. What's the leading force for Q? Think of the direction. Well, it's 3mg and the T holds it back. So 3mg minus T. And the same sort of thing going on. Kind of confusing that you have F equals ma, and then you have m as an unknown there. And when you have these two here, have a think about what you could do if we're trying to find the acceleration. Well, we need to get rid of that t there. The m's The m's, don't worry too much about those. You'll find that they often cancel in mechanics quite a lot. So just keep them there. Well, if we add them together then, t plus minus t, that's going to disappear. 2ma and 3ma is 5ma, a little bit like we saw with the connected particles earlier. We end up with simultaneous equations, and this is our final sort of equation, put them together. So minus 2mg plus 3mg is mg, and 5ma. And like I said, often the m's are not a problem. You can see here that they cancel out. So A is going to be g, which is 9.8, over 5. That's your acceleration. So as long as you know to put a direction on it, and you make an equation about each of the particles, add them together, you can find your acceleration. Find the tension in the string. Well, the tension is the same throughout. This t is the same as this t, is the same as this t, is the same as this t, because it's a light, inextensible string. So the tension's the same throughout. So you need to use this A here with any equation that has t in it, and you can find an answer. So let's see if we have a nice, neat version. So you could rearrange this if you wanted to. And when you know your A, you can put your A in there. G, you can put G in. So look, you can find your tension. It did say in terms of M, so there's still an M there. That's fine. Find the force exerted on the pulley. Okay, so now finally we're going to get to the pulley. So this pulley here, what are all of the forces acting on it? Directly acting on the pulley itself. Well, I can see these ones here, but there must be something else going on. Otherwise, wouldn't it just be accelerating to the ground? So let's take a look. We have the tension here. Oh, it does say, doesn't it? Find the force exerted on the pulley by the string. So it doesn't say like resultant force or anything like that. It doesn't say about the reaction. We just need that T and then that T again. So it has T down on the left and T down on the right. So that's the force acting on it by the string. It's not the resultant force, it's the force by the string. So adding those two together. And finally, find the distance traveled by Q. So that's this one here. So it's going to go down, isn't it? In the first 4 seconds. So what do we have? We have a U equals 0 from before. We have a T equals 4. Hang on a minute. We have an A as well, don't we? It sounds like a SUVAT question. And because acceleration will be the same throughout the question, and it will be constant, it is a SUVAT question, okay? So for the last part here, find the distance. A equals 1.96, T equals 4. You can use S equals UT plus half AT squared to find an answer for that one there. The force questions involve working out acceleration, so it's quite common that once you find acceleration, they might turn into a bigger SUVAT problem. Any modeling assumptions used? Yes, lots of them. Okay. The light string meant when we looked at the whole system, there was no mass. Inextensible string meant acceleration was the same throughout. The smooth pulley meant there was no friction. Something along these lines. Okay, so there you go. And that's how you sort of do the pulley questions. So now you're ready to have a go at them.